Now let's look at three pictorial or graphical examples. I drew three functions on the board, none of which is continuous at x equals 0, although I haven't defined what continuous means. This is three reasons why a limit would not exist at x equals 0. This one, which I tried to make this look like f of x equals 1 over x, the graph, well, it's not defined at x equals 0. So the function doesn't need to be defined at x equals 0 to have a limit, but the limit doesn't exist here because it's unbounded. When you get near 0, the function is unbounded. So if I took something like 0 plus 1, 0 minus 1, which is just 1 and negative 1, in this region, the function is unbounded. And the reason is the limit does not exist at x naught equals 0. So for all of the three of these examples, I'm using the x naught equal to 0. And one thing I should have mentioned, this x naught, if you notice, 0 is an accumulation point of the domain in each of these cases, right? The domain, I made it look like the domain is maybe all real numbers except for the number 0. Well, actually, on this one, the domain would be all real numbers because f of 0 does have a value. So there's no way, there's no capital M where I could get this function bounded in this region. Now, in this one, if I go out, it looks like I went out a little bit more than 1, but I'll just call that 1 and negative 1. It's easy to find a bound. What could I use for my capital M in this case to show that it's bounded? What capital M could I use? Well, the obvious one seems to be use m equal 2. And if the absolute value is less than or equal to m, that simply means that the whole function is bound between 2 and negative 2, which it is in that little interval there. On the third one, it looks very similar to the previous problem. It is very similar, only this time the m equal 2 will not work because the function is defined at f of x equals 0, at f of 0, or it's defined at 0, but f of 0 is equal to 4. So in this case, I would have to bump it up to m equals 4, or any number bigger than that. So this would be the case where we were looking at the maximum in that proof. This explains why we had to use the maximum of the L minus 1, L plus 1, and then this little straggler point right here. Now, if f of 0 happened to be down here, we could have used the same value of n as we did in the previous example. So this is essentially the three types of discontinuities that we've talked about. This one is unbounded in this interval. There's no limit at x equals 0. This one has a limit of 2 at x equals 0. The height of the graph approaches 2 as x goes to 0. And the same for this one. This one is what we would call a removable discontinuity, if you remember that from calculus. If I just fill that hole in, I've got a nice continuous function, and the limit would exist everywhere. And this is called, I think that would be called a jump. I'm not positive. That might be called a jump discontinuity here.